thing that I would have everyone think about. For those of you that are the old timers in the room, this is sort of super simplified here, but we're looking to observe changes over time of voltage in a circuit. So sort of how does it work? Well, there was a device that was invented back in the late 1800s called a cathode ray tube. And I want to take you just real quickly, without burning up a lot of time here, because most of the folks in the room understand this. I want to go inside of the cathode ray tube for just 1 minute and make sure that everyone in the room fully and completely understands sort of what's happening at the most basic level. Some of the older scopes that are in here actually have cathode ray tubes in them. The cathode ray tube is a glass envelope, as we call it. It's a glass enclosure, completely sealed, devoid of air. It has a vacuum inside of it. And inside of it, inside the rear of the cathode ray tube is the appropriate mechanism so that if we feed a high voltage into it, it creates a beam, a very narrow beam of high energy electrons that move from the back of the cathode ray tube toward the front. Because we've said it's a sealed glass envelope, it's devoid of air, and one of the frontmost surface, on the frontmost surface, that's where this high energy electron beam is projected onto. It's a very tiny pinpoint beam, and the inner surface of that glass tube is coated with phosphor in such a way that so that when those electrons strike it, it emits some light so that we can kind of see it with our eye. So to simulate that and to also just really absolutely clearly convey so there's no uncertainty among anybody in this room what we're talking about, we're going to go inside a cathode ray tube just for a second. What I have here is my green laser pointer. I'm going to actually shine on that wall and try not to get this in anybody's eyes here. So we're inside of a glass envelope, a glass housing, devoid of air, total vacuum, no air inside of it. We have a high energy voltage source that's causing an electron beam to be projected from the rear of the tube to the front of the tube, and there's phosphor on the front of the tube that allows that electron beam to present visible light to our eyes. What I have here in my quick and dirty little mock-up here are some simulated plates, as we call it. Imagine, if you will, that each of these white pieces of foam core is a metal plate, and that we have two that are oriented in the horizontal orientation and two that are oriented in the vertical orientation. And you can see that I've identified those plates as being sort of mated pairs, if you will, by the fact that there are wires attached to the left and the right in the horizontal that sort of go together, and there's a red and a black wire that go to the vertical plates, these metal plates. We're imagining this, if you will. So we have two wires going to the vertical plates. And one thing that we know about electron beams, high energy beams that are traveling in a glass envelope devoid of air, is that that beam can be deflected. The beam can be moved around in terms of where it actually, where the beam actually strikes the front of the glass cube. That can be changed by changing the voltages on these four plates. If we were to take a battery, for example, and apply it across these two horizontal plates, apply energy, electrical energy across these two wires so that one becomes more positive than the other, then the beam will be deflected. Okay, it'll be deflected and move in one direction. Same thing with the vertical plates. If we have the beam just dead center of the tube and we apply a DC voltage across these two plates, that beam is going to be deflected either up or down depending on the polarity of the voltage going into these plates. So this is sort of the most fundamental mechanism that's inside of the CRT-based oscilloscopes, and it was this premise that scientists in the late 1800s discovered and allowed them to manipulate this beam around the tube by changing at various times the voltages between the horizontal plates and the vertical plates. When the oscilloscope was first invented, it was a novelty. It was a novelty for almost 50 years. It was a curiosity, almost like a lava lamp, or like those little things you get at the mall that have the plasma balls. Thank you. So for many, many years, it was considered interesting, a novelty. You could sort of display how, the physics of the electron beams and to make it visible. But it wasn't until the mid-1900s that folks started trying to realize that, hey, we're building circuits that are becoming more and more complicated. We need ways to be able to visualize what's happening in these circuits, and felt the need to start developing the technology for oscilloscopes. So there were oscilloscopes even in the early 1900s, primitive ones, but it wasn't until really the mid-1900s that the graticules that we see on these, the ability to actually have specific X and Y demarcations were added. And here again, it wasn't until 1946 that the concept of triggering was introduced into the oscilloscope market. And it was at that point that Tektronix was formed, and the two guys that formed it just really started pushing on that triggering concept, and they began producing amazing oscilloscopes, and of course the rest of the history we know from there. It just kind of took off from there, and just Tektronix is one of the world leaders in oscilloscope technology. So I just want to make sure that everyone understands we have horizontal deflection, we have vertical deflection in a system like this. In the old CRT-based oscilloscopes, this is precisely what's happening. With this simplified version, there's a lot more going on inside. But nowadays, because we have LCD screens and TFT screens, it's practical to eliminate the physical high voltage requiring CRT and simulate the same sort of functionality in a device that resides totally in the digital domain, where we have a digital display and no longer need the CRTs. So the oscilloscopes that are in this room, as you look around the room, there are some that are CRT based and some that are not. So a variety of different types. Well, I say that. My LCD based one may actually be not with me here. All of them may have CRTs in here. So that's the general concept of an oscilloscope in terms of how sort of the general premise of what's going on inside of it. So now, how do we kind of start to work down through some of the details of what's going on in these different oscilloscopes that we have? There are really, I guess, four primary systems to any oscilloscope. You've got a display, whether it be CRT or LCD or whatever it is. You have a horizontal sweep generator that's generating, establishing our time base. You have a set of vertical amplifiers of some sort or another in there, and you have a triggering mechanism. And by manipulating those, each of those different components within the oscilloscope, you can allow a waveform to be displayed. So having said that, a bit of background, so that just make sure there's no, are there any questions about that first piece there that is pretty basic? I know a lot of you sort of.
I presume they're working oscilloscope have more than one set of points.
These probably, Dale may know that. Some of the oscilloscopes in there may have multiple sets of plates. I know there's at least four, but once in all the ones that are in here, there may be more. I don't know.
I don't think so. You just need
four. I mean,
you need two pair, a horizontal pair and a vertical pair to do deflection. Okay. Now there's other structures in the tube to do focusing, but as far as deflection, there's just two pairs.
Well, I have a question.
Okay.
So in a television, there's a sweep across where there's always just a series of horizontal sweeps and a vertical sweep, making a sort of a rasterization. But does that happen in an oscilloscope, or is it a vector-based display where it just...
Oscilloscope is vector-based. And TV CRT doesn't have any deflection plates in it. It's magnetic deflection. It's a thing called a yoke that slides on there, and there's four coils, two of them in the vertical, two of them in the it's magnetically deflected.
They could have made a TV that had plates, but the thing is, the neck for a plate-driven system has to be much longer than one using the yoke system. Coiled yokes can deflect a beam a lot more than an electrostatic plate can. So you can shorten the tube length in a TV set by using yokes.
You can't use a yoke when it's a fan.
Can we get a low sweep rate and just kind of show? Can we get no?
There's one that'll do a low sweep rate.
Slow sweep rate. So just to clarify, if anyone still, this may be a good deal to give you guys. Some of you don't kind of know a lot of what's going on here. That's some great comments there. So here you can see on an analog oscilloscope, this is something a digital scope won't do. I can't put it.
I'm sorry.
Hey, Jamie. Hey. Oh, okay. Thank you. Okay, thanks, Jamie. So for those of you, just to sort of give you a visual representation, you can actually see if we slow down the horizontal sweep rate on here, you can actually see that electron beam that I was just talking about sort of stand very across the screen. And then what's going to happen here, as we've basically established a sort of a metronome almost in there that can be adjusted by speed that determines how frequently the horizontal sweep sweeps. We can change that. We can make it very fast or very slow. And as that sweep is occurring, if a voltage is introduced to the vertical amplifiers in the system, then that beam will be deflected up and down and create waveforms. That sort of all makes sense? So we have, when I was, the first oscilloscope I ever played with, was when I was 13 years old. One of my Boy Scout leaders let me borrow his Heathkit oscilloscope, and I played with it for a month. He let me have it for an entire summer. I had to return it back to him. But at 13, I was really struggling to understand triggering and exactly getting I always struggled to get the waveforms exactly synchronized to where they need to be. So I wanted to make sure that was all kind of clear to everyone. So, so here we have, I'm going to take this display off in a minute. You can see on this Tech digital scope here, I've got an arbitrary waveform generator attached to it and had the AHRC logo as best I could. And back to your question, because an oscilloscope is purely a vector-based device, you can't backtrack. You can only, the sweep only goes in one direction, and as you create deflection in the vertical axis here, you can't go back.
So that's why there's no bar.
So that's why when you try to imagine how to create a letter, I mean, I can't do the horizontal bar here because it would make these other upper portions of the A disappear. We can only sweep from left to right, and we can only deflect up and down. So in order to create this sort of, this is the best I could do on the HRC logo, I'm using the arbitrary waveform generator, but maybe that'll help to sort of clarify in your mind. So let me turn that off, and then let's actually go with, so here again, so now that everyone's sort of got the basics down here, what's happening, that we have a sweep generator that's sweeping, in essence here, on these oscilloscopes built after the 1950s. They all have what's called a graticule. The graticule is this sort of XY grid that we see on the oscilloscope screen, and the graticule gives us a visual representation of whatever the time base is on the oscilloscope, or it allows us to basically make measurements according to where our time base is set and based on what our voltage is set at. And what I mean by that is that these one individual square on this graticule does not always represent the same thing. Certain types of meters that we play with, you know, if there's a change in the meter, it sort of always represents the same thing. But on an oscilloscope, it's up to the user to define the meaning of this individual square on the graticule here in terms of what it's representing. Go ahead.
One thing maybe that might help them understand better. Basically, your time base controls how long it takes to get from the left side to the right side. So if you're looking for low frequency stuff, you might only take 1 millisecond to go all the way across. But if you're trying to look at things in the megahertz range, you might take 10 nanoseconds to go across. So that beam, the speed it travels across, as Clint says, you control depending on what frequencies you're trying to identify.
Exactly right. So here again, we have inside the oscilloscope this horizontal sweep generator that's allowing the beam to sweep across, and then we have the vertical amplifiers that allow it to deflect up and down. And because, as Lynn has pointed out, we can change the sweep rate, then you can imagine in your minds that we can dictate to the oscilloscope how much time we want this distance to represent, or how much change in voltage we want this vertical distance to represent. So we're representing changes in time in the horizontal, changes in voltage in the vertical. An oscilloscope is said to operate in the time domain. And without getting too crazy with it, that's as opposed to other instruments like the spectrum analyzer I have at home. It produces a similar sort of display, but this operates in the frequency domain. So the x-axis represents changes in frequency, not in time. An oscilloscope, the x-axis represents changes in time, the y-axis represents changes in voltage. On a spectrum analyzer, the x-axis represents changes in frequency, and the y-axis represents changes in intensity of the signal. So an oscilloscope is said to operate in the time domain, and so that sort of gets back to what Lynn was saying. And so now we all see that all these oscilloscopes have tons of knobs on the front of them, And in essence, as we make changes to the knobs to control the sweep rate or the amount of vertical deflection that occurs based on a voltage input, the reference point that we should always have in our minds is the one graticule unit. As we're making changes, in this case, this oscilloscope is currently set to 50 millivolts per division. A division is, once again, the space from edge to edge of one square that you can you see with the display with the laser here. So in this case, we have 50 millivolts per division. So a deflection on the trace, the image that you see on an oscilloscope is frequently called a trace, meaning this whole picture from left to right on the screen is called a trace. And as we view the trace on the screen, in this particular instance, a deflection up would represent 50 millivolts, a deflection down would represent a negative 50 millivolts, a deflection of two of the graticule increments on here would represent 100 millivolts. In the horizontal, we now said that an oscilloscope operates in the time domain, so now we know that we're representing time in the horizontal. We've said that a number of times. I'm a big believer in what Zig Ziglar says, that repetition is the mother of learning, so some things I repeat over and over to make sure everybody really understands it. So we're operating at 100 microseconds here on this. Our time base is said to be set to 100 microseconds. So that means the sweep rate from this point to that point is 100 microseconds. The sweep rate between two graticule intervals here is 200 microseconds. By making changes to my to the horizontal time base on this oscilloscope, you can see down at the bottom that I'm changing the time base here, and now I have the time base set to 1 millisecond. 1,000ths of a second is now the time interval of sweep between these 2 points. So I'm in essence changing the snapshot in time, if you will, of what the oscilloscope is actually displaying on the screen. I can also likewise change the vertical interval here. Just move it to 100 millivolts. I can change it to 200 millivolts, and so on, and go up to 1 volt. And of course, you'll notice here. Let me just disconnect this probe altogether from the frequency generator. And one interesting thing, you can see now that I'm set to 10 millivolts per division, very, very tiny fraction of a volt per division, and now you're starting to see a trace appear that has a squiggly line on it, but yet we're not attached to anything. The input to the oscilloscope is not connected to anything. So now what we've done is we've brought the range of the oscilloscope down to such a sensitive level that it's just simply displaying the ambient noise that's present in the test leads and just sort of in the immediate proximity of the oscilloscope here. You can sort of see a little bit of 60 hertz kind of embedded in there, and then just some noise in general. So you can see that it's possible to drive the vertical amplifiers to a point that they can amplify just even noise that exists. When you get into these very sensitive voltage levels, the noise can become very difficult to remove from them. Certainly. It may decrease them or it may not, depending on, I mean, we may be experiencing this just simply from wiring that's, up in the, you're welcome to try if you want real quick and do an experiment. It might possibly decrease it, but probably not, because the lights over here are off, and all the conduit and wiring that's run through the space here and so forth. There's going to be some 60 hertz sort of noise kind of in the ambient present all the time. So as you go to those really sensitive levels. So, okay, now we've talked about vertical. It is, and
Okay.
I'm hoping that the little stopper's still in there in case someone else needs to come in. Okay. So just a real simple sort of thought here, and make it sort of easy to visualize. I'm going to take a battery, and because we've now established in our minds that we have this horizontal sweep thing going on, and we have the ability to deflect vertically, what I'm going to do is, we're set to 1 volt per division. Let's actually take it to half a volt per division. So, and let me actually jump. I had this thing kind of set up earlier for. Actually, that probably is enough. Let's see if this. So I'm taking a battery. This is the input to the oscilloscope here. I'm going to connect this battery across. Make sure I'm set to. Make sure I'm not loosely coupled there. If I can wiggle and jiggle here, so many hands on fingers, I can get moving at one time here.
Oh,
Hold on. Let me get stabilized here. Okay, so this is, as we said earlier, we're really trying to measure change in a system. That's the real benefit of an oscilloscope. Well, in this case, I just simply took a AA battery and I put it across the scope probe. How much change is occurring here? None. There's no change occurring outside of the fact that when I touch the battery, I struggle to try to get the contacts on. So this is sort of a static circuit. There's 1.5 volts coming out of this, a little more than 1.5 volts coming out of this nice fresh battery we just took out of the package. And now you can see that in the vertical, that beam was deflected up, and we know that we have a vertical scale of 500 millivolts for division. So if you were to measure, we have 1, 2, 3, and a little bit more divisions. So we're actually, if you were to convert that to a voltage, we're, what, about 1.75 volts or so is what's actually coming out of this battery. So that should give an even clearer indication of sort of what's happening there. If there's a, so now you can imagine that if we introduced a dynamic sort of signal into this, that we're going to be able to display that as well. So let's go back to sort of the tried and true signal that we're all most familiar with, the sine wave, kind of the so in this case, this is a repetitive waveform. It's actually a sine wave at 1 kilohertz. So what we're saying here is that it's a sinusoidal waveform, and let me figure out where I'm triggering at here. Let me use the cheat button here real quick. So now we have this very stable, really nice reproduction of a sinusoidal waveform, and we can sort of take a look at it here and learn some things about the waveform. We see that we're set to 50 millivolts for division, so we can see that the sinusoidal waveform is going on the positive side by 100 millivolts, then going negative 100 millivolts, and so on. And of course, I can confirm that, but from the function generator, I'm set to 100 millivolts peak to peak. Peak to peak means from the very top to the very bottom of one cycle, and we can sort of see that here.
You know what annoys me about digital scopes is all that noise on there that really isn't there. On an analog scope, that would be a very stable, pure sine wave with no jiggles on it. But a digital scope, it's got all that ratty stuff on it. I don't know why that is.
I've always assumed it's just due to the sampling mechanisms,
Must
whatever,
be.
just whatever. So Dale's brought up a great point here. There are two fundamental types of oscilloscopes that exist in the marketplace. There are analog oscilloscopes and digital oscilloscopes. The analog oscilloscopes that have the CRTs in them, like this kind of venerable old PET 465 here, it has the electron beam that we talked about earlier, the cathode ray tube, it has the plates and the beams being deflected and so forth. And that beam is, the presentation of that beam on the screen is very pure. As Dale's pointed out, there's no noise, it's a beautiful, clean, crisp trace. And yet I'm displaying a very similar signal over here, and we're getting all this sort of choppiness. What's happening on here is sort of purely the deflection via the plates that we talked about earlier. On a digital oscilloscope, the concept of how it functions is different. It's actually bringing in an analog signal, a signal that's changing radically over time, and it's sampling that signal at some interval. And that interval on most of these scopes is adjustable. So it's basically on a digital oscilloscope like the one that I'm using here. Yeah, and so Dale's got a nice presentation here of a sine wave that's stable, no noise, perfectly clean and crisp, and yet this one's got the heebie-jeebies over here. It's kind of bouncing all around. The way that a digital scope operates is it essentially takes a sample in time. So we're feeding the input of the oscilloscope this analog waveform, this constantly varying waveform, but the oscilloscope, what it's doing internally, because it uses digital memory and a microprocessor and all the things that go along with that, it's actually starting at some brief moment after this, kind of at the beginning of the screen here, taking a sample to see how high the voltage is at that instantaneous point, converting that to a number, plugging that into a memory location, and then going slightly over to the right and taking another sample, and then coming slightly over to the right again and taking another sample, and so on. So a digital oscilloscope is essentially just taking little snapshot samples in time and converting all those into numerical values, storing those numbers, and then recreating sort of kind of on an old dot to dot. You know, we've all done the, you know, with your crayons and, you know, dot to dots kind of thing. The oscilloscope is making its best effort to take all that digital information that it's accumulated and convert it back into a presentation that our eyes can associate with, that our brains can associate with. It's trying to recreate this waveform. So digital oscilloscopes are very dependent on how fast the sampling rate occurs and how many samples per second are you actually taking in order to reconstruct this waveform to determine how accurate it is.
Are you able to speed up your sweep and zoom in at all and see any steps on the waveform?
It's always going to do that.
So you're
I mean, you can't zoom in far enough to where
No.
oh, if it changes up there, you got 250 kilosamples per second now.
the voltage up here a little bit too.
Oh, yeah, you're right, you can see this.
Okay, you can kind of see steps.
And of course, the weaker the signal is, the more jittery it's going to be naturally. But
Well, I think part of that is real noise.
yep, maybe a small part of it's real noise, but it's digitization sort of junk that's going on there.
Well, one
So-
limitation is going to be what's the resolution of the A to D of that digital oscilloscope.
Exactly,
I mean,
that's a big
A
part of it.
lot of oscilloscopes don't go beyond 12-bit resolution. So that's the reason why in an analog, there is no A to D chip. You're seeing live the effect on those plates, how far things have moved. You don't have a digital converter guessing, is it this bit or that bit?
Right.
12 bits should produce a beautifully smooth waveform. I've really tried to figure it out in my own head. Can't. I don't know where it's coming from. But clearly, I mean, 200 millivolts per division. That's a pretty. That's
It's a strong enough signal that it really
That's
shouldn't be very noisy.
exactly. Shouldn't have any noise in that at all.
So it is. It's some artifact, just the way these things operate.
Yeah.
So
Well, the thing is, on 12, the A to Ds, like say you've got a, you may not be using the full 12-bit range there because that signal might only be, say, 20% of the full range of your A to D because your A to D may not be scaled depending on your
Well,
gauge.
it should be scaled to the top and bottom of the screen.
Well, depending on the scope, maybe it isn't. A cheaper scope might not do that all scaling. You may have one set range and you can change the gain.
But if it was scaled to the top and bottom of the range, you'd have 4,096 points, which should be invisible to the naked eye. I mean, like HDTV times 4.
it is interesting how different oscilloscopes have different personalities, and there are times that an analog scope can be much more helpful at looking at a certain type of waveform than a digital scope. They each have their benefits. One cool thing about a digital scope is that you can save the waveform. You can actually, on most digital oscilloscopes, you can actually, like a PC, you can sort of stop the processor if you had to, remove the signal source, and the image stays up on the screen just the way it was. You can't do that on your typical analog scope. So there's pros and cons kind of both ways. On a digital scope, you can save the trace to disk or to memory of some sort and copy it. This will save the images, bitmaps, or whatever you might need to do.
If you leave the signal on a CRT long enough, it'll save it.
Exactly. Go let you burn it in.
Yeah.
So,
Permanently.
So we've talked about the horizontal sweep rate and the fact that we can change it. We've talked about the vertical controls, controlling the vertical amplifier to establish different voltage levels per division. Let's talk about the triggers for a little bit. That's where things can sort of start to get kind of crazy, trying to understand what exactly is going on. So in some of the earliest oscilloscopes back in the 1920s and 30s, before Tektronix developed the triggering mechanism, basically the sweep system inside the oscilloscope was always in a free-running mode, meaning that once you establish the time base for the oscilloscope, the trace would sweep from left to right, and if your signal wasn't exactly in synchronization with it, or it kind of was what it was. It would display the trace, but the traces were frequently very jiggly and would move to the left and the right on the screen and not really be synchronized to anything. So when Tektronix developed this concept of triggering, they said, hey, instead of just having this free-running sweep oscillator that is that's creating this causing the horizontal deflection on the CRT, let's add an additional circuit inside the oscilloscope that allows us to set a user-definable voltage threshold at which point it will reset the sweep and cause the sweep to refresh, cause the screen to blank and the sweep to refresh. That's the concept of a trigger. And you can imagine how incredibly useful that is, especially if you have a waveform that has some erratic features to it. The ability to trigger on something that is not consistent. So let's explore just basic triggering for a second, and let's go back to the HRC logo that we were looking at here a little while ago. Take me a second to reset this back up. So I'm gonna recall the HRC logo that's saved in this arbitrary waveform generator. It's let me location 4. Let's see. Okay, and of course, the downside to a digital oscilloscope, once you stop it, like I stopped the process just a minute ago, you have to remember, oh, I better restart it, because I'm sitting here looking at myself thinking, why I wasn't displaying anything? Well, the oscilloscope is in stop mode. We'll put it back in run mode. So now, all right, let me fiddle here for 1 second. So now we have all these HRC things on the screen here. Let me do something here. Kind of get, well, let's see what to do. Let's do this. Okay, so, and I'll change the time base a little bit just to make it more interesting. So it's clear to all of us that there's an HRC logo in there, but they're all moving back and forth so fast we can't really tell what's going on. And the reason for that is I've disabled or put out of range the oscilloscope's trigger. So right now the sweep generator is sweeping. It's doing exactly what it's in the time base that I told it to be in, 200 microseconds per division, but it's just free running. So now we want to make it, we want to somehow make this image more stable so that we don't get vertigo and have to run to the bathroom here. So let's you can see that there's a pointer down the lower right hand side here. On this particular oscilloscope, that pointer represents the trigger, meaning that once a voltage waveform is in line with that arrow, the oscilloscope will begin to trigger off that waveform. I'm going to move it up, and now you can see that the behavior is sort of changing here a little bit, and I can sort of improve the situation, somewhat. Well, it's helping. It's still a little bit kind of herky-jerky, and it's kind of off to one side. The AHR is to the right, and the C is kind of off the other. So now the sweep generator now knows that we would prefer to trigger off of part of the voltage in this waveform. But where on the waveform are we triggering? I mean, are we triggering at the second half of the A or the middle of the H? Where is it triggering? Well, right now, to be honest with you, I'm not exactly sure because it's sort of kind of bouncing all around here.
Isn't it where the T
Oh, there you go. Thank you. Yeah. Okay. So it is. It's right where the T is there. So we can change the trigger voltage threshold and sort of clean things up a little bit. So that shows one benefit of a trigger, but there's another option that most oscilloscopes have, and that's multi-channel oscilloscopes, I mean. This particular oscilloscope has 4 input channels, and on most oscilloscopes that have 2 or more channels, you have the option to trigger off one of the other channels, to actually be displaying a waveform that's being presented to input number 1, but be triggering off of some other event that's occurring attached to input number 2. So I'm going to actually do that here real quick. On this particular oscilloscope, when I go to the trigger menu, which is where I'm at right here, down on the lower left here where it says source, I can press that button, and now I can establish what I'm triggering off of. I'm going to trigger off channel 2 here, and this particular arbitrary waveform generator happens to have a synchronization output, which is attached to channel 2. So when I take the trigger off channel 2, basically, if we were to look at channel 2 just by itself, I'll just add that to the waveform here. This is the violet there is the synchronization pulse that's coming out of the sync output of this arbitrary waveform generator. And you can see that now I'm triggering off of that, and now the HRC logo is perfectly dead stable, and I can move it to exactly where I need for it to be on the screen without interfering with the content of the logo, or having one letter come at the beginning and one at the end, or whatever. So being able to trigger off of another input is an option on even analog or digital multi-channel oscilloscope. A number of the oscilloscopes that are here in the room, especially the analog ones, have a number of other features on the controls. One is called delayed sweep, and this is something that Jebediah, yours should have. Probably both of us have. So delayed sweep means that we're going to accept the trigger event in, and we're going to refresh the screen off the trigger event, but we're going to create. And Dale, if I say this wrong, let me know. We're going to wait some period of time before we allow another trigger to come in. So delayed sweep is the concept of we have all these components in our waveform. We allow the oscilloscope to trigger off one of those events. It blanks and refreshes the screen and displays that image. And because maybe there's some other artifacts that come after the first, or maybe there's a big gap before the next, we want that oscilloscope to forcibly be made to have a delay introduced in the triggering mechanism before it allows another sweep to come in. It basically closes the gate, says no more triggers are going to happen for however much time you program in, and then it'll, once that window back opens again after the time frame you established, it'll allow another trigger to come in. So that's the concept of delayed sweep, and on a lot of these it's done via a series of knobs that are in the front of the unit. One interesting thing about some of these analog scopes, on the digital scope here, it's said to be calibrated, meaning that this instrument has been calibrated by a test lab, and it's known to be accurate for the vertical deflection and for the horizontal time base. It's known to be, that half a second is really half a second, and half a volt is really half a volt, and there's no change in that. There's no debate about it. A lot of the analog oscilloscopes, like this really powerful unit here, it can be calibrated too. It should be, and probably has been at some point in its life. But one of the kind of cool features of these analog scopes that's not available on the digital scopes is that you can zoom into a waveform. You can put the vertical amplifier into what's an uncalibrated sort of mode and zoom in on some tiny artifact that's in an analog waveform. And basically you can, it's calibrated, but you can undo that by pulling the red, or the red knobs to talk about the cal. So on a lot of the older scopes like the one you have, you're going to see, for me, for a number of years, it was confusing why it said cal and uncal, or had these knobs that you could pull them. What the intention of that is it allows you to sort of muck around with the amplifiers inside of it and sort of be able to zoom in on a signal, but you're not exactly guaranteed that the deflection or the time base is going to be accurate anymore, but you're just trying to, you don't really care that it's an exactly accurate representation over time or voltage. You just want to kind of zoom in and see what in the world's going on in the circuit. So you can throw these into this uncalibrated sort of zoom in mode, and you can't do that on a digital scope. It's just not an option. You're strictly not.
Way back in the 60s, my first, I think it was an Oscope 460 or something I had when I was a teenager, did not have triggered sweep, but of course it would still synchronize the waveforms, because what it basically had was an oscillator, sawtooth generator for the horizontal sweep, variable frequency, and a sync circuit in it, so that it could synchronize to some multiple or sub-multiple of the signal you were trying to look at. So you could adjust that frequency of the horizontal until it locked in. It would stay locked, and you have a certain number of waveform patterns across there. But you didn't really know what the time really was. It was kind of like in uncalibrated mode all the time.
Okay.
And it had a little thing about frequency about it, so you get a general idea, but it was like my dream to have a triggered sweep scope that I could actually get horizontal time measurements out of, because this thing was so crappy. But it wasn't, like like you were talking about at the beginning about the Tektronix inventing triggered sweep. Yeah, that was great, but the other scopes would give you a stable waveform. You just didn't know what the exact time was.
Okay. That's very interesting. I didn't even know that that existed back at that time. So it was sort of another set of oscillators that you could sort of beat against whatever's coming in.
Oscillators, all it was.
And you could
tune it until it found some harmonic.
I see. Very interesting. Okay, I never had heard that was available. So we've now gone over. I'm trying to see where we're at on time here. We've now gone over. I want to make sure that there's enough time for everyone to ask questions about their own oscilloscopes. And as I mentioned earlier, there's a ton of folks in the room that know a lot more about this than I do. And there's probably some questions I would have for some of the other folks in the room. So we've talked about horizontal sweep, vertical deflection, what a trace is, that we have a graticule, that we have horizontal time base and a vertical deflection level. We've talked about being able to trigger off different, not only different channels, but trigger off various voltage levels within an individual waveform. So what else would it make sense to cover? Okay, digital storage. Okay. Okay, so let's play with something here for just a second. So this particular oscilloscope is one of Tektronix's. They call it a digital phosphor oscilloscope. It's one of their more advanced digital storage scopes. Now, of course, this is sort of a moldy oldie here. Myself and a friend of mine were buying these off eBay a while back and repairing them, swapping out all the capacitors. It's just an interesting point of note. I bought probably 5 of these. But in its day, this oscilloscope was probably $25,000 to buy new in the 1990s. We've been typically buying these off eBay for $500 to $800. I'm trying to remember if this exact one. I've bought a bunch of these over time. But typically what we discovered, Barry Ward, another guy that loves knows who figured this out, if you buy one of these scopes and take the processor board out, and it's a big processor board with a lot of stuff on it, and take the entire front panel apart and replace every single electrolytic capacitor on all the ports, it all works. The whole thing. The scope, basically, you buy it, you swap out all the caps, you let it do a self-cal, and it's back up and running.
That's a great idea.
So we've repaired a bunch and we sold them, and then I kept a handful of them for myself here just to play with. But so these can be had for not a huge amount of money. There's about 77 capacitors you have to replace, and I have really good, I use one of the Metcal Talon sets of tweezers to get all the caps off, and we're going to swap them out. So okay, so this is a digital phosphor oscilloscope, which is one of Tektronix's more current. The scope is not current, but that technology is still produced to this day in their small lunchbox scopes. I'm going to put this scope in digital phosphor mode for a second. And what digital phosphor mode does, and I'm going to get back to Frank's point here in just a minute to make sure everyone understands just the DSO sort of concept in general. But Tektronix's digital phosphor concept is that there's a multicolor screen that basically can show sort of a heat map, if you will, of a waveform. It can show you sort of, in essence, how long the dwell time, I guess is the best way to view it, sort of how long the dwell time is at any given point in the waveform according to the color. So you can see that the red represents where the trace is, dwells for the longest periods of time within the waveform, and the lighter colors, blue and yellow and others, are areas where there's either a very fast rise time, a very fast fall time, or some other, more brief portion of the, so if, in the case of the HRC logo, it just makes it look interesting. In the case of certain signals where you're really trying to understand a signal that's occurring very fast, it can help give you a sort of more easy to visualize picture of what's going on. So that's the digital phosphor concept. But let's jump back now to the digital storage, the digital storage concept, the most powerful feature of this particular oscilloscope. As we mentioned earlier, this oscilloscope runs on a microprocessor. It has memory. It boots up. It can have firmware updates made to it. It has a clock and all these different things in it. All the things you would normally associate with a system that had a microprocessor in it. And we've also seen earlier that I can stop and start the system and basically freeze the trace on the display here. So let me think of the best way to show what I'd like to show here next. What I'm going to do, I want to show that the most powerful feature of the digital storage oscilloscope is its, in my mind, correct me if you have something else in mind, is its ability to capture a transient waveform, a waveform that occurs very briefly in time, to be able to have the oscilloscope sort of be looking out for it, and when that, and you can sort of set up a series of trigger events, and the oscilloscope, when that trigger event is executed, it'll trigger and then stop, all by itself without any other human intervention. It's a really amazingly powerful feature, and I use it a lot to try to figure out what I messed up in the circuits I'm putting together. So let's fiddle with that here for a minute. I'm going to get rid of the HRC logo for the time being. We're going to turn off we'll turn off channel 2. We're going to get back to just one trace on the screen. So we have just channel 1, and that's all, nothing else. All right, give me a second to remember how to set this up. Let's see, let's go to, all right, first of all, I'm going to make sure, I'm actually going to use, this oscilloscope has an internal, all right, let's see that. Let's actually do, I'm sort of going to get it kind of configured. This oscilloscope has an internal probe calibration element in it. I'm going to make sure to talk about probes here in a minute. I think that's a critical subject when you're talking about oscilloscopes. Let's have a little note there. Okay, so here's what we're going to do. I'm going to put this particular oscilloscope into what we call acquire mode, and I'm going to put it into a single acquisition sequence. So this mode that it was in up here where it says run stop button only, that means that this oscilloscope is going to keep on sweeping, keep on triggering, only until you turn off the power or hit the run stop button and stop the oscilloscope. But there's another option. The next option is single acquisition. Whoop, I just triggered it with my static here. So single acquisition event, it sort of demonstrated itself. In single acquisition event, the trigger level was previously established by kind of wherever I happened to have it left before. So there's the trigger. And then essentially, the oscilloscope is going to go into a mode where it just doesn't sweep, it doesn't display anything, it just is sort of waiting for a trigger event to come in. And once that trigger level is breached, it creates one trace and one trace only, and then stops all by itself. So now, in order to...
Before you, that's a good example of what you just talked about. Not only did it trigger, but you see it went back in time, which is the real power of the storage. You see how it triggered right dead center, but it captured the events prior to the trigger.
Yeah,
So not only did you see your trigger, but you saw what caused the trigger. In your typical analog sweep, you start where the T is. You can't go back in time because it's always sampling and it has this moving memory. And then when the trigger says, well, how much do you want to display? So it's like a moving digital window, like a digital, and then you say, I want it right here. You can see back and forth in time. Kind of what you have right there.
That's an excellent point that he brought up, that it does. This particular oscilloscope, you can establish, you can tell it how long of a record link, if you will, you want it to capture before and after the trigger. Because it has digital memory in it, it's constantly sampling the incoming information, and you can sort of tell it how far back in time you want it to remember and how far forward in time and how much you want it to display. And so let's trigger it again. Let me undo that. Whoop. But it's triggering. I think I need to sort this thing out here and get all this, just some noise. Well, of course, plus I'm set to a really All right, so we're back in the single. I'd forgotten that the scope actually keeps on the screen what last happened. I'm going to be real gentle this time, try not to breathe too hard. And I'm going to touch the oscilloscope probe compensation signal on here. All right, so this oscilloscope has a probe compensation output that allows you to calibrate your probe. We'll talk about that more here in a minute. That all oscilloscopes, you need to be mindful to probe. So, so what essentially happened is it triggered on the first cycle of this square waveform, and now, as we talked about earlier, I can go back in time. Of course, there was nothing. It was just, in this particular case, it was just a DC level until it received the first input pulse from the square wave. And now I can also scroll to the right and look, further down, and I can also change the record length. I can make this record length be dozens or hundreds of individual screens worth of information to the prior to or afterward.
So the T on the top, is that kind of like your time range?
So that's where the T. Oh, I'm sorry. Yeah, exactly. Yeah, I'm sorry. I thought you were talking about the trigger. So up here, exactly. What this is a sort of a visual representation of how much memory I've told the oscilloscope to use, and where the screen, these two brackets here represent the viewable screen from left to right, and the dotted line represents the entire memory capture that it was just taken. So, whoops, I hit the wrong button there. So you're right. If you and you can see the relationship between the T for trigger and the T for trigger here. As I move toward the left-hand side of the screen, the left bracket represents the left side. They're both getting toward the edge of the screen. Well, now the trigger is off the screen, and now I'm looking at the continuation of that record forward in time. I actually have the scope currently set up to view a very narrow window of time. This particular oscilloscope has a lot of memory in it, and it can store literally dozens or hundreds of screen widths worth of data, and then you can scroll back and forth. But it takes so long to scroll back and forth that for normal use, I would keep it to a pretty tight range here. This one will output it. You can print the file, save it as a bitmap, those kind of things. You can save it as a native text file, but I don't know if you can. I don't know the answer to that.
Who has a floppy disk stored on it?
Yeah, it can use a bitmap is a common way that I save files. If I'm trying to
Which is unipolar.
if I'm trying to email something to a friend and help me figure out a problem, I'll email it to a bitmap kind of thing. So
To make sure I'm on track, if I remember correctly, we're using the trigger to figure out like once the voltage hits a certain peak. And so the idea is if you're trying to read your inputs from your robot or whatever you're building, once you see it picking up, then you know it's got a signal. So you know if the source is on or off. Like if you're doing a line problem, you know from the black or the white line. And so you're trying to figure out the amount of time, and then actually see what kind of signal it is. And like if it was like through a serial port, it's
you can. On these scopes, I've pretty frequently taken the serial data coming out of the serial port and decoded it on screen, figured out what letter of the alphabet or what text characters were coming out. So you're right. The trigger point, it's essentially an arbitrary voltage choosable by us, by the user, at which point the oscilloscope is going to blank and redraw the screen for you. The trigger basically causes the screen to be redrawn, and because you can control where that trigger event, what the trigger voltage is, you can sort of forcibly cause the oscilloscope to have on a repetitive waveform to have a very stable display of it. So if you have a line follower, thing you're working on, you would be looking at the output from maybe the infrared LEDs, or if you had an amplifier that those LEDs or the pin diodes, whatever, feeding into. You would be able to monitor that and kind of just tell if your sensors are kind of doing what you expect them to be doing or not.
Think of it as just a greater than or less than. You can choose whether it's looking for anything above that threshold or anything below that threshold.
Right.
It's just like a conditional. Is it greater than or is it less than? And you choose which one you're looking for. When a value goes above it, when it's greater than, or if the value goes below it when it's less than.
What I'm saying too is you can, capture a certain time frame. So that you, like if you're looking for particular signals like from the serial port or reading the character, you can capture in that time frame and you can actually see what your signal
Yeah,
to see what.
Let's talk about the trigger a little bit more, maybe actually do some more demonstration here. So, let me, what am I doing here? Okay, let me get back to run here, let me get out of the,
things. One thing I've done in the past, I've set up things where I would put a debug point where I set an I/O in my code and use that as a trigger, but I would set my buffer up so I'm looking at what happened before that trigger on other data. So I can have one bit I was watching, I wait for the trigger, which is a signal from my processor, and then go look at the data in question that brought me to that trigger. You can do things like that.
okay, let's explore the trigger in a little bit more detail just to make sure this is really clear here. So, so right now, my trigger point is displayed as that arrow right there. It's also numerically quantified down here on the bottom right. So my trigger is currently set at 120 millivolts. By changing the trigger level, you can see that I'm increasing where that arrow appears on the screen. I'm basically increasing the trigger voltage. I'm increasing the required trigger voltage for the oscilloscope to redraw the trace. So as I turn my trigger voltage up, you can see that it's increasing or decreasing. And you can also see that the intercept point for this sine wave here is moving. Because this arrow represents my trigger level, just to give me a visual representation of it. This gives me a quantified representation of that trigger voltage, but in real life, that's exactly where the trigger is occurring, where that T is. That block T right there is the literal exact trigger that we're using at this moment. So so the oscilloscope's using that instantaneous moment in time to cause a screen blank and redraw of the trace. So as I drop the trigger voltage, it's starting the draw of this sine wave at a different point along the sine wave. If I move it down to 0 volts, if I can possibly hit, I'm not sure if I can exactly hit 0 volts. I'm -4, I'm at 0 volts. Right now, my trigger point, the oscilloscope, we're telling the oscilloscope to blank the screen and start drawing this image starting at a 0 volt, at the 0 volt crossing here. So that's what's actually happening here, is this image is actually starting to be drawn from that point forward. But as Frank mentioned earlier, and it's an excellent point, because this is a digital storage oscilloscope, it's digitizing everything coming into it. It knows what just happened also. This is sort of what just happened because it's still in memory, but this is the trigger point. And on an analog oscilloscope, all you're going to see is from here forward. You're not going to see all this previous information that's stored in memory on the scope. So that's the trigger point. Now let's try to make this maybe a little bit more clear. Right now, we are triggering on the rising edge of a sinusoidal waveform, and our trigger point is 136 millivolts. So in reality, this oscilloscope is starting to execute the trigger from that point and going forward to draw this trace. What I'm going to do here to maybe make this a little bit clearer, let me figure out what I'm doing here real quick. Exactly. We're going to play with the slope. What we just said, what we've established here, is that we're presently triggering on the rising edge of a sinusoidal waveform at 184 millivolts where I just moved it to. What I'm going to do is go down here to my slope control, press that button, and I'm going to tell it, instead of triggering on the rising edge, I want to trigger on the falling edge. Look what just happened to the trace. Now instead of starting here and going up, we're catching it on the down. This is like the mind bender at Six Flags or whatever. Now we're on the down side here. So what I just did is I told the oscilloscope to now trigger on the falling edge of this sinusoidal waveform and trigger on the falling edge 184 millivolts down. Is that right, Dale? I mean, essentially, no, I'm sorry. I'm sorry. Yeah, it's still positive 184 I'm sorry. Yeah, it's still positive 184. Yeah. Thanks. I had a little mental gyration going on there. So now we've told the oscilloscope to only trigger on the falling edge of a signal and trigger, but still trigger at positive 184 volts. So now you can probably imagine in your mind, as I drop the trigger voltage down, let's make it a negative number. So now the oscilloscope is starting to draw the trace at negative 228 millivolts. If we were to, if this were an analog scope, that's all you would have on the screen. You would have nothing more, because the trigger point on the analog scope is defined as the left part of the left origin on the screen. Does that sort of help?
Well, no, what I was thinking of is like if you're trying to read a signal coming in from an infrared, or like for your line phone, right? So, I can't remember the direction, but if you're on the white space, and I think it's at 0 volts, when once you hit black, it's going to go up to the on.
You'll have some change. Yeah, if it's a
I'll have
digital
change
sensor.
in the,
Are you talking about like the QTR sensors? Is that what you're
Yeah,
looking at?
yeah.
They make two versions. They make an analog and a digital version of that sensor. Let's assume you have the digital version that's designed to go straight into an I/O on a microcontroller.
so then
But
once it
you're right.
goes up, then the trigger would start
In
drawing
that
it
case,
at that
with the
point.
QTR sensor, the digital version of it, you're exactly right. If you're monitoring that signal output from that QTR module, black, I forget which is which, but one is going to be a high level and the other is going to be a low level. On white, it'll be one level, and on black, it'll be on a different level. Is that?
Exactly, and then once the trigger, once it sees that voltage, whatever it is, then it will start tracing it.
Correct.
You gotta think about what that signal's doing. When you cross the edge of the line, it'll go from nothing to something.
But when it goes to that something,
And
then it triggers.
it'll trigger, but it's only gonna jump up or down, whichever way you got it set. It's not gonna change like that because you crossed the line. It's like a one-time event until you cross another line.
Right,
So it'll jump up and it'll stay there. It'll be like you did with the battery.
right, until you get into the white area. No,
Right,
but,
and then it'll change back, so.
Okay, so let me, I want to just describe one other thing real quick. I know I'm kind of bouncing around on the oscilloscope here, but I want to talk about coupling on the input just for 1 second to make sure everyone's clear. And I definitely want to allow everybody to have time to talk about their own scopes here. We're already at 11:16. So let me talk about coupling and the probes, and then I'm going to shut up and let everybody just start working on their own scopes and asking questions about them here. Okay, right now this oscilloscope is configured for DC coupling. And what that means is that we have this AC sinusoidal waveform on here. I'm going to lower the vertical deflection here and get this waveform to be a little bit smaller. And on this particular waveform generator, I have the ability to add a DC component to this waveform. Whoa, that was too much. So, so what I've done, let me go to. Actually, give me a second here. Okay, so this is still that same, whatever it was, 500 hertz waveform that we're looking at earlier, but I've added a DC component. Basically, there's a sinusoidal waveform, but it's riding on a DC voltage level. You can see from where the location of this channel 1 indicator here is,